Hello, welcome to the very first lecture of Essentials of Quantum Optics. You know that optics is a branch of physics which is devoted to the study of light. It explores how light is emitted, transmitted, reflected, refracted, and absorbed, as well as how it interacts with matter and other forms of electromagnetic radiation. In general, when we talk about optics, we understand classical optics. In fact, most of the phenomena that we encounter in our day-to-day life as regards light is concerned, classical optics is good enough for its explanation. However, with the advent of quantum technology, we now know that classical treatment of light is no longer adequate, and we have to treat light quantum mechanically. That means we have to study light at the level of photons. When the study of light is done at the level of photons, this is known as quantum optics. Quantum optics combines the principles of quantum mechanics and electromagnetic theory and study light at the level of individual photons, and in the process it comes up with numerous applications. Let us begin our discussion of quantum optics by revisiting some fundamentals of quantum mechanics, and first we are going to study the quantum mechanics of two-level atoms. So let us begin.
A two-level atom is the simplest system in quantum optics. It consists of a ground state and an excited state. The ground state is represented by this Kate notation. Here ground state is represented by Kate1 and the excited state is represented by Kate2. I will talk about this notation a little bit later, but maybe most of you may be already aware of. Or sometimes this ground state is represented by Kate0 and excited state is represented by Kate1, and this is the usual notation that is used to denote qubits in the context of quantum computation, by the way. Or sometimes people use to represent the ground state by this notation, say down state, down, and this is excited state is represented by up state like this. In fact, any two-state system, what we are actually dealing here, when I say two-level atoms, I mean to say two-state system, and the discussion that we are going to do in this particular lecture is going to be valid for any quantum mechanical two-state system. Or sometimes this ground state is represented by, when specifically we talk about atoms, this ground state is represented by Kate Z and the excited state is represented by Kate E. So in this lecture, as I said, we are going to stick to this particular notation. Alright. By the way, as I said, this particular notation is called Dirac-Kate notation. Dirac-Kate notation. And with this notation, one of the postulates of quantum mechanics which says that all the information about the quantum system or the quantum particle is contained in this function called the wave function, right? All the information, whatever you want to know about the quantum system is contained in this wave function, or as per the Dirac notation, all the information about the state is contained in the state vector Kate psi. This is state vector. There is a subtle difference between the state vector and the wave function. For example, you know that if I take modulus of psi of x square, in fact psi of x square dx from basic quantum mechanics, you know this gives the probability of finding a particle or a quantum system, between two position x and x plus dx. Now this wave function psi of x is related to state vector Kate psi as follows. this is equivalent to projection of the state vector on the coordinate space. Okay. And if I talk about momentum wave function, say phi of p, then this would be basically the projection of the state vector on the momentum space. And as like mod of psi of x squared dx, mod of phi p square dp gives the probability of finding the momentum of the particle. This gives the probability of finding the momentum of the particle or the system, quantum system, particle between two values p and p plus dp. In this lecture, or in fact in this course, we are not going to use wave function notation much. We are going to use the state vector notation, and this Dirac notation we are going to utilize. Okay, now coming back to the two-level atom, the atom may be in the ground state or it may be in the excited state. So if we don't make any measurement, we have no idea whether the atom is in the ground state or in the excited state. So in fact it is in an arbitrary state, and mathematically it is represented by say k psi. So the atom may be in the ground state or it may be in the excited state. So this is represented by this equation. So Az is the amplitude coefficient of the ground state, and Ae is the amplitude coefficient of the excited state. So the arbitrary state of the atom can be represented by this state vector, where I am writing the state vector as a superposition of the ground state and the excited state in such a way so that mod of Az square, which gives the probability of finding the particle or the atom in the ground state, and mod of Ae square gives the probability of finding the atom in the excited state, and the total probability should be equal to 1. So this is the constraint, you can consider it as a constraint for this state vector. Az and Ae should be such that mod of Az square plus mod of Ae square is equal to 1. By the way, we can define a dual of this state vector psi as bra psi. I'm sure this is also and in that case this particular equation here can be the corresponding equation for bra psi, can be represented as bra psi is equal to Az star, which is the complex conjugate of the complex amplitude Az. Then this kz is going to be represented by bra z, and Ae would be now Ae star, and Kate E is going to be bra E.
Now, if you want to derive any information about the two-level atom or two-state quantum system, you have to make a measurement. You have to make a measurement of the quantity for which you are seeking information. Now, you know that in classical mechanics, for every physically observable quantity in classical mechanics, there is a corresponding operator in quantum mechanics.
For example, as you know, position is a classically measurable quantity, position x. So its corresponding quantum operator is x cap, x with a hat. Similarly, momentum is a physically observable quantity, and in quantum mechanics it is represented by an operator p cap. Then say energy E, which is also a physical quantity, and in quantum mechanics it is generally represented by the symbol h with a hat h. It is called a Hamiltonian, and so on. There are many physically observable quantities, and corresponding to them there is a operator in quantum mechanics. So if you want to derive information about the system energy, you need to make a measurement of energy which is equivalent. Mathematically it basically amounts to applying the operator Hamiltonian operator to the state vector k psi. And if you do that, because the state vector psi contains all the information about the two-level system, if you apply the operator, the energy operator, then you will be able to know, because of the measurement, the atom will go to either the ground state kg or to the excited state ke. So, and mathematically, that's what we are going to get after making the operation, basically applying the operator on the state vector k psi. Then it will go to k psi will go to either kg or kt, and corresponding probabilities are, as you know, is going to the ground state. The probability is mod of az square, and the probability that it is going to the excited state is given by mod of a square. In fact, this kg and ke are the so-called basis vectors or the basis states of the two-level atom. This is akin to writing the two-dimensional vector A. Say we generally write this two-dimensional vector A, its component as ax along the direction of x, and other components say y, ay along the direction of y, right? So a vector can be represented in terms of these unit vectors x cap and y cap. You can also consider kg and kd, kt like that, but the analogy ends there only. And also these basis vectors kg and ke satisfy some eigenvalue equation. For example, if the Hamiltonian operator is applied on the kg, then you are going to get the state again kg, and it would basically multiplied by a number, and that gives the energy. Ez is the energy of the ground state. And if you apply the Hamiltonian operator to the excited state, basically the kte, then you are going to get the kte once again as a result of this operation, and it is going to multiply by number ee, and this is basically the energy eigenvalue of the excited state or energy of the excited state, right? So as you recall that we have this ground state and the excited state, the corresponding energies are ee for the excited state and ez is for the ground state. Moreover, you know that this basis states kg and kt are normalized. So what I mean by that this particular relation, this is scalar product of kg with bra z is equal to 1, which is actually, if I talk about wave functions, in the case of the wave function, kg is going to be represented by this wave function psi z, and bra z is going to be represented by this wave function psi z star. And then if you take the integration over the volume, then this is going to be equal to 1. So this is the representation of in the wave function terms, but in state vector, that's what we write. Okay, and similarly for the excited state, kt bra e, this scalar product is equal to 1, and these states, basis states kt and kg, they are orthogonal to each other, and this is represented by this equation. Again, you can make the analogy here in terms of the unit vector. For example, you know that x dot x unit vector, that's equal to 1, y dot y is equal to 1, and x and y are orthogonal to each other, so dot product is, or scalar product is basically going to be equal to 0. So these are the things that you actually know even from the so-called elementary quantum mechanics. Now you say, in fact, this state vector psi itself is normalized. Maybe I have already told you, and you know it, that k psi, the scalar product of k psi and bra psi is equal to 1, and corresponding in terms of the wave function, this is basically psi star of say x. If I write it in the coordinate space, psi of x dx is equal to 1, right? This you know from your basic quantum mechanics. Now, one can utilize matrices heavily to do mathematical calculations, and you know that this state vector psi can be represented by a 2 by 1 matrix or a column vector, if I am dealing with a two level atom or a two state system, and this operator, any operator, arbitrary operator A, say this operator A, or even for the Hamiltonian operator H, it is going to be represented by a 2 by 2 matrix. I'm sure you know, so that's why I'm just mentioning this. For example, this ground state Kz, ground state vector Kz, is represented by this basis vector, column vector 1 0, and this Kate E is represented by this column vector 0 1, which is it has 2 rows 1 column, so 2 by 1 matrix. And in that case, this state vector, arbitrary state vector psi, which is a superposition of the ground state and the excited state, it can be represented by using this notation for the Kz and Ke. I can write this state vector in as a column vector that is going to be simply Az and Ae. So it's going to be simply a 2 by 1 matrix. In fact, you can very quickly see the power of this mathematical formalism, because if K psi is represented by this, that corresponding its dual, that is bra psi, is going to be represented by a row vector where the row elements are Az star and Ae star, right? So this is a basically one row and two column, and this state vector Kate is represented by 2 by 1 matrix, 2 rows 1 column, and the bra, corresponding bra, is represented by 1 by 2 matrix. So it's a row vector. Now if I take the scalar product of this bra with the psi, then it is simply amounts to multiplication of this row vector Az star Ae star with the column vector Az Ae, and if you do the matrix multiplication, you can immediately see that this is going to give you Az mod square plus Ae mod square, and as you know that this has to be equal to 1, and thereby you see that implies that this state vector, arbitrary state vector psi, which represents the arbitrary state of a two-level atom, is getting normalized. So matrix multiplication and this manipulation is going to be, we are going to exploit it throughout the course quite heavily. Now coming to the case of the operators, as I said, if I am dealing with a two-state system or basically a two-dimensional vector space, which is also called the two-dimensional Hilbert space, this operator A can be represented by 2 by 2 matrix, and its elements are, say, A, B, C, D. Okay. In fact, there is a theorem from linear algebra that becomes quite useful to represent these operators, and the theorem in linear algebra, it says that any arbitrary 2 by 2 matrix can always be, just let me first write it down and then I will explain. Any arbitrary 2 by 2 matrix can always be written or expressed in terms of four matrices sigma x, sigma y, sigma z, and identity matrix I, where sigma x, sigma y, sigma z are the so-called Pauli matrices, and sigma x is defined as 0, 1, 1, 0, sigma y is equal to 0, minus I, 0, sigma z is equal to 1, 0, 0, minus 1, and I, that is the identity matrix, is 1, 0, 0, 1. So in terms of this, you can actually represent this arbitrary state, not arbitrary state vector, I was talking about these matrices, these matrix A with elements A, B, C, D, you can express it in terms of these Pauli matrices like this. Say A0 sigma X, A1 sigma Y, A2 sigma Z plus A3 identity, and you can very trivially work it out by some trivial calculation. You can show, maybe we'll do it in the problem solving session, you can show that A0 is equal to B plus C by 2, A1 is equal to I into B minus A by 2, A2 is equal to, you can do it, it is very simple, it's straightforward, A minus D by 2, and A3 is equal to A plus D by 2. Now let us look into the Hamiltonian operator of a two-level atom. Say its energy levels are arranged in such a way that the ground state energy Eg is equal to 0 and the excited energy Ee is equal to capital E. And the excited energy state is represented by kT and the ground state energy is represented by kg. But we can always shift the energy levels in such a way that the ground state I can put at Eg is equal to minus epsilon z, and the excited state I can put it as Ee is equal to plus epsilon z. What I am doing is that I am just taking the reference level at say E is equal to 0 now, where I am just 0 I am taking as my reference level, and then I am shifting the ground state by some amount epsilon j below 0, and the excited state I am taking it by energy plus epsilon z from this reference level 0. Okay, so it has some merits, as you will see what we are doing. The excited energy state is again represented by kT and the ground state is represented by kg. So we are now going to use this particular configuration to write the Hamiltonian for this two-level atom, and in fact you see that this enables us to write the general 2 by 2 Hamiltonian in this particular form. I have epsilon z in the and minus epsilon z in the diagonal, and epsilon x plus I epsilon y, epsilon x minus I epsilon y in the off diagonal. And you can immediately see that this has to be the form, because this Hamiltonian, this is an operator, this Hamiltonian has to be, this matrix has to be Hermitian, and you know that any quantum mechanical operator has to be Hermitian because a Hermitian operator has real eigenvalues. Now when I am having my Hamiltonian in this particular form, it's extremely easy to write this or express this Hamiltonian in the form of the Pauli matrices. So what I can do, I can immediately, or you can immediately actually see that this Hamiltonian, let me not write this hat all the time, so just let me write this h, thereby users understand that I am talking about a quantum mechanical operator. This Hamiltonian I am writing, and this Hamiltonian in terms of the Pauli matrices I can immediately write it as epsilon x sigma x, epsilon y sigma y plus epsilon z sigma z, right? And hopefully it is very easy to see, because let me remind you once again, and you can make it out very easily, that sigma x is equal to 0 1 1 0, sigma y is equal to 0 minus I 0, and sigma z is equal to 1 0 0 minus 1, right? I hope you can see that yes, I can express this matrix in this particular and very compact form, and in fact I can further compactify it. I can simply write h is equal to epsilon dot sigma, because this sigma is the Pauli vector, and it has it has the components sigma x, sigma y, sigma z, and this epsilon, it components are, I can consider it as a vector with the component epsilon x, epsilon y, and epsilon z. So this is a very powerful way to express the Hamiltonian, and it has several merits, as you will see maybe in the next class, that a general Hamiltonian for a two-level atom, when it is isolated, it can be expressed in this very simple form, h is equal to epsilon dot sigma. And by the way, these Pauli matrices have several properties, well-known properties, which you can immediately, very trivially, it can be proved that sigma x square, by the way, let me just once again write that these are actually Pauli operators. Sigma x square is equal to sigma y square. These are the properties you can verify very easily by just doing the matrix multiplication. Sigma z is equal to identity. So again you can see, so that sigma x multiplied with sigma y, it is going to give you I into sigma z, and maybe we'll do it in the problem solving session. And then the commutation between the operator sigma x and sigma y, I hope you know the commutation relation. This basically means that I have sigma x sigma y minus sigma y sigma x. If you do the matrix manipulation, you are going to get it as 2i into sigma z. And similarly for all others, for example, if you have sigma y sigma z, this matrix commutation is going to give you 2i sigma x. Then again you have, say, sigma z sigma x, this is going to give you 2i sigma y, right? So these are important relations. And also these Pauli matrices, they actually anti-commute, and you can show that sigma x sigma y, they anti-commute with each other. Anti-commutation relation is simply, it would be sigma x sigma y plus sigma y sigma x. This is going to be equal to 0. Okay, and you can write the similar relations for all others in the cyclic order. If I take, say, sigma y sigma z, that is going to be equal to 0, and sigma z sigma x, this is going to be equal to 0. These are very useful relations, and we are going to utilize it.
Let me end this first lecture here. We are going to continue our discussion of two-level atoms in the next lecture. We'll study the geometrical representation of the quantum state of two-level atom or two-state quantum system by using the so-called block vector formalism. And it is of tremendous importance in quantum information science. So see you in the next lecture. Thank you.